The E7 error is appearing on this higher PCB, and due to this, the unit has completely shut down. Now, let's check what the fault is. I tried cleaning it with a blower, but it hasn't been cleaned, and there's a lot of accumulated dust on it. However, we'll clean it later. First, let's try turning it on. I attached a reactor because it won't turn on without it. Now, I'll provide it with power. The second LED turns on, so I turn the unit on. When I provide power, the second LED turns on, but after a short while, the first LED should also turn on. Now I'll clean the first LED a bit to see. If the first LED doesn't turn on, it means there's an issue in the PCB, and I'll explain where exactly that fault might be. Earlier, I mentioned in a video that in some PCBs, the problem lies in the relays. If the small relay isn't functioning properly, it will cause issues. However, this PCB has only one relay, and the main electric flow that comes during the initial startup is what I'll show you now. First, we turn off the power supply. After turning off the power, we discharge the system, meaning we'll remove the electric charge. For this, I use a soldering iron. I connect it here, and once connected, the system discharges, and the light gradually fades out. Now, the first thing we'll do is clean the dust off the PCB, as this is an important step. On this PCB, you can see there's a relay installed, which is a switching relay, labeled as K5. It handles the switching when the SMPS, switch mode power supply, is functioning properly. If the SMPS is not working correctly, the switching won't occur. However, this relay ensures the system runs smoothly, particularly the compressor, so the system can handle the load. If the load isn't managed by the relay and is directly applied to the system, it could lead to a fault. This is because if a problem occurs, the PCB or microcontroller won't be able to control or turn off the system. To solve this issue, the company installs a PTC, positive temperature coefficient sensor. What happens is, when electricity initially flows into the system, it passes through the PTC. The benefit of this is that if there's a problem in the system for any reason, the PTC will heat up. After that, its resistance will become very high, and the system will disconnect from the electricity. This is the advantage here. Initially, when electricity flows into the system, the main LED2 turns on. The reason this LED is on is due to the capacitors and the small PCB inside, which contains the IPM PCB with a bridge rectifier that is functioning properly. However, the SMPS is not working correctly and is not turning on, which means the microcontroller is not controlling anything. The first test conducted is to check whether the chopper or switching IC is receiving the 320 volts of electricity or not. Upon checking, there's a power MOSFET labeled IRFUC20. The resistance R14 on this side is receiving positive voltage of 300 volts, which is connected to the first auxiliary winding. Let's check at this point, which is the source. First, we check how many volts are coming to the source. It's showing 322 volts, which means the voltage is reaching the MOSFET. Now, let's see if this voltage is reaching the drain or not. For this, I'll attach it to the drain side, but the drain side is not turning on. There are no voltages here. This means we need to check the IC properly. To do this, we'll take ground from the switching IC. The ground is present, so we'll take it from the capacitor. Now I'll check pin number 5 to see if voltage is coming through there or not. Pin number 1 is the starting point. If I check pin number 5, I should get around 8 to 10 volts, but I'm getting only 184 millivolts there. The voltage at the gate side of the MOSFET is absent. In this situation, it's possible that the switching IC itself might be faulty, or the feedback might not be functioning correctly. How can we determine if the feedback is faulty? Generally, the switching IC operates at a speed of about 66 kilohertz. The speed is so high that it's beyond our imagination, so when it first turns on, if the switching IC is okay, it performs a test and turns on if the feedback is received properly. This makes the system stable and the electrical components turn on, meaning that the chopper starts generating the supply and then the entire system turns on. But if for any reason the feedback is not received, the system tries again 4 to 5 times and then it shuts down. It will not turn on again until the electric supply is cut off and restored. After that, the process repeats. If there's a problem, this cycle keeps happening. Now, to determine whether the issue is with the feedback or the switching IC itself, we first need to check the voltage on pin number 6, which comes from the VCC and is essential for the IC to operate, and pin number 4, which is the ground. We'll check both by placing the black probe on pin number 4 and measuring pin number 6, where there should be voltage from the VCC. Here, you can see approximately 7.78 volts fluctuating, which means voltage is reaching the VCC, so the problem could either be with the feedback or the IC itself being faulty. Now, what decision should we make? We need to address the feedback issue or decide whether to replace the IC. Since the speed of the IC is so high, it completes its task in just a few milliseconds. First, we'll work on the feedback. If the feedback is not proper, the IC will keep hanging and won't function correctly. Therefore, we'll check the reference IC to see if it's working properly. The reference IC is TL431, which is a programmable precision reference. We'll first check the reference IC by looking at its cross-section. If we see some voltage there, we can identify the problem. Currently, the system is showing 0.46 volts, and it's trying repeatedly but failing each time. This suggests that the IC is repeatedly trying but failing. We'll also check the optocoupler, IC2, and its anode and cathode. If there's voltage there, the issue might be with the reference IC. The system will need to be discharged and repowered. We've checked that 1 volt is present at the anode of the reference IC, but no voltage is appearing at the output, which indicates that there might be a problem with the reference IC. So, let's change the reference IC and see what happens. I removed the AZ431 reference IC and replaced it with the TL431A. I'll install it in the position and turn on the power. I'll wait a bit to see if it turns on. If it still doesn't turn on, I'll check the voltages again and review the feedback voltages at the anode and cathode. If it's still not appearing, and there's no output either, the PCB is now completely fine. But let me explain the issue. I turned on the power, and you can see that the power LED is on, the LED 1 is also on, and the relay has switched, which means the PCB is okay. After a while, errors started to appear, and the system began to blink. It's blinking 12 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When it blinks 12 times, it indicates that there is no sensor detected. Since there is no sensor installed, I can say that there is likely a fault with some sensor. The current issue is that the outdoor ambient temperature sensor is missing, which is why it's blinking 12 times. However, the main thing is that our PCB is now on and working fine. Let me explain what the fault was and check the voltages again so you know if you need to troubleshoot it in the future. Earlier, there was a small fault in the voltage we were checking, but I couldn't understand it at first. However, once I properly understood it, I was able to fix it. When we were checking the reference IC, one side was showing 0.5 volts. So let's check here and take the ground from here. As you can see, it's showing 2.43 volts on its reference. Now let's check how many volts are coming on its output. As you can see, it's showing 1.01 volts. Let's also check the optocoupler, and it shows exactly 1.01 volts. But the key point to observe and learn here is that the voltage is stable at the moment, which is why there's no problem. If it were unstable and fluctuating, it wouldn't be proper, and that's why the IC wasn't turning on and the voltage wasn't passing through. Now, what was the problem here? Let me show you. First, let's check the voltage on pin number 5. I'll take the ground from this capacitor from E3 and check on pin number 5. Earlier, there was no voltage here at all, but now we're getting around 1.12 volts, and there's absolutely no fluctuation. Similarly, on the VCC, the multimeter is showing us 10.65 volts. Earlier, we were seeing a maximum of around 7 volts, and they were fluctuating, which means the system was turning on and off repeatedly. But why was it turning on and off and not staying on properly? That was causing the problem. Now, where was the issue? It was in this capacitor. If you look here, there used to be a black capacitor, and when I checked the voltage earlier, it wasn't right. Now I've replaced it with a blue capacitor. This capacitor is from E3, rated at 22 microfarads and 50 volts, which I have now replaced. And if you look at it, visually and even in its testing, there's no obvious fault. But as you saw, the voltage was actually dropping and fluctuating. This is the capacitor that I replaced, rated at 22 microfarads and 50 volts. So I'll check it with the multimeter now. As you can see, it's showing a maximum of 15.7 microfarads, which is much lower than its original value. The acceptable value should only drop by a maximum of 10%, but it should still be around 18 microfarads. However, it's gone down to 15, which is why the problem occurred. This capacitor has weakened and was no longer functioning properly. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.